Okay, so this topic is unique. Usually, if we were in school, we would have, you would have in-class assignment on a weak acid or with a strong substance titration question, because the math here is a little bit, well, you'll see how long it takes. So if you printed the note off, most of it is filled in. And what you're just going to add is the little things that I write and the color things, the explanation parts. So what I'm going to do for your assignment, because I think even to try it on your own might be a little bit challenging. So you'll have to do a weak acid or base, like an ice question all by itself. You'll have to do a titration with strong all by itself, but not the two of them together. Okay. But the theory part of it might help you with your explanations. So still go through the lesson, but actually some of the math will be fine. It'll be just the last part, once we get to equivalence point, that things start to get a little bit out of control. Okay. So there is the principles that we talked about in grade 11 are still the same. Equivalence point is still when, by definition, when the moles of acid and base are equal. But in this case here, when you have something that's weak, it is not going to be at a pH of 7. So the principles about a titration curve are still the same. So if you have this sharp peak, then the midpoint is the pH at equivalence point. But you can see here that it's no longer 7. So what happens is you're going to see that because when you have a weak substance, then its conjugate is a legitimate either acid or base, which means it'll either donate or accept protons. So then the presence of the conjugate at equivalence point is going to mean that it's going to shift the pH. So here we have a strong base, so NaOH, and a weak acid. To start, how did I know that? So again, here the pH is acidic, but not super acidic. And as always, with a weak substance, you'd be given the Ka or Kb value. So some people will think, oh, it's above 7, like on the basic side. So here it's 9, right? So that's a basic pH. And people will say, oh, the strong base is making it basic. And it's actually, when you have a weak acid, you get a conjugate base that will legitimately accept protons, making the pH at equivalence point higher than 7. So it really has more to do with what happens when the weak acid dissociates than the strong base itself. Could you do a weak acid base with a weak acid base titration? For sure you could, and then the math would even be one level farther. Okay, so it just depends. You just have to deal with all the data separately. So we're going to do the same thing. So we have in our flask is going to be acetic acid. So we have volume of acid and concentration of acid, and then we are adding base. This time I made the concentration of the base different so that you can see where the numbers are coming from, hopefully a little bit better. Okay. So in the burette is sodium hydroxide. So you can see here in this curve, we're adding base to the acid. So initially, we have no base, just like before, whereas in the strong titration, you could have just calculated pH right away. However, when you have a weak substance, whether it's an acid or base, you have to do ice. And then again, you would be given the reference value, the Ka or the Kb. Okay, so, oops. Oh, I forgot about this. Hopefully, I think your note's okay. So when we're doing the weak acid only. So plus water makes the conjugate base. And H3O, we have 0.2. No water, cross it out, 0, 0, plus X, plus X. We're going to use the 100 rule. like I said, your textbook in this case loves to use the 100 rule. So products over reactants. Okay, I'm just going to go over here. My iPad's a little weird in the formatting. So 1.8 to the exponent, or times 10 to the power of negative 5 times 0.2. And then square root. And we don't care about the negative root because you can't have negative concentration. Okay, so now we have X, which is H3O plus. And we can now find pH. So this question, like I said, you're going to have to be able to do ice questions where, similar to this one, where there's no titration to it, but this is like from the very first day. So pH is low, but not super low, okay? All right, so now onto our weak base. And now we added some acid, 10 milliliters, so same as strong, we're gonna add them together. So once we start adding base, you're gonna consider the equilibrium and neutralization separately. So here's the neutralization reaction. So we have acetic acid, which is the weak acid, and the strong base makes the conjugate base, and of course water. And so these two are what's going to be important. The sodium here, I wrote it like this so that to emphasize the presence of the conjugate substance, like this anion here. Don't really worry about the sodium. It's a spectator ion. It does not influence pH, so that's not important, okay? So what happens with the big problem with these types of titrations is once you start having the neutralization reaction occurring, so once you start adding the base to the acid, you can see here that the substance that I've highlighted, the acetate, the CH3COO negative, that's also found in the equilibrium ice table. So that makes a big difference. Now it's like a common ion, right? So we're not gonna have 0 anymore. We have to use an actual concentration. But we'll do the neutralization math first. So similar to what we did with strong, you have to calculate the initial moles. So there's the initial moles of acid. So just like with strong, they don't change for the substance in the flask, whether it's an acid or a base. And then you calculate the moles of base added. So again, that's exactly the same. You subtract to find out how much acid is left once neutralization has started to occur, and you divide by the new total volume. Okay, so right up until here, we've already done this kind of math. So in the red, it says if this were a strong acid, we could just now do the concentration of unreacted acid, this value here, and find the pH, right? We would be done. But because acetic acid is weak, it doesn't dissociate 100%. So now we have to not only take this new concentration here, this number here, and we have to put that into our ice table. So when, so that went down here. I'm just gonna skip for a second, okay? All right, but we also have, again, there's that neutralization reaction. So now we have this conjugate base being produced by the neutralization reaction. And similar to what all the problems we've been doing before, it's going to be 1-to-1. So again, another level to the math could be that you would also have to do stoichiometry, which again is like probably even beyond first year chem. Okay, so many of you are not going to have to deal with that. Okay, so the amount in moles of the conjugate produced is the same as the moles of the substance added, so the base, because the coefficients are 1-to-1. That's a 1, sorry. Okay, so the moles of base are equal to the moles of acetate Again, it says it there because some of the acetate is produced by the neutralization reaction. So we just calculated the moles of base to be, on the other slide, 3 times 10 to the negative 3 moles. But in an ice table, we need concentration, so you divide that by the new total volume. So now that number that's produced, if you want to use the same highlighter color, it becomes 0.1. So it's no longer 0. Why? Because it's similar to the common ion effect. Okay, so if you print the note off, the Ka stuff, like solving for X, is on the other slide. I do use the 100 rule, so if you on this slide want to write that down. Oops. Now this number is even smaller, so for sure it's going to work. And then here you want to do the same thing. We're basically ignoring the X values. Okay, so now over here, we've got the same equilibrium constant expression, products over reactants, except this time this acetate is 0.1, and then you solve for X. So now the hydrogen ion concentration is getting smaller, which means the pH is getting higher. So this is less acidic, which makes sense because we're adding base. Okay, part C says calculate what equivalence point is. So again, the principle about moles, so this is technically moles of acid and moles of base. When are they equal? That is the same. That's the definition of equivalence point. Just remember, so that's all we did last year in grade 11. Remember then, this is not going to be at a neutral pH of 7. Okay, so you get 13.33 milliliters. Okay, so here's really where it starts to get a little bit hairy, okay? So at equivalence point, do the same thing. You get a new total volume, okay? We're going to use that number. So at equivalence point, all of the acid has been neutralized. Oh, I forgot an arrow here. So this neutralization reaction is complete. It is not an equilibrium reaction, so it goes, it would go 100% to the right. So all of the acid, this does not exist anymore in the neutralization reaction. All of it has been converted into its conjugate base. So if this was a strong acid, strong base, let's say we had this. Oops, sorry. Then these are not, they're not good conjugates. And water if there is no other pair to go with it, there's nothing to donate or accept from, then it's going to be a perfectly neutral solution as well. So that means that you get a pH of 7 at equivalence point. Whereas here, all of the acetic acid has been converted into acetate. This means the moles of acetic acid have been converted into an equal amount of moles of acetate. Again, it's 1-to-1, okay? So I've just showed that there. So the initial moles of the acid were 4 times 10 to the negative 3. So now I'm just going to read the red, okay? Acetic acid is weak. It does not dissociate 100%. So equilibrium is going to be established like we have to do ice. That means its conjugate base, which is acetate, is a legitimate proton acceptor. So it will have an effect on the pH at equivalence point. So it's going to be higher than 7 because the conjugate is basic, okay? If it were a weak base, then it would be a conjugate acid and the pH would be lower than 7. Okay, so you take the moles and you divide by the new total volume, similar to what we've been doing before. Now, here's something that's a little bit weird, okay? We're going to be considering the conjugate base equilibrium. And so what that means is because all of the acid has been neutralized and it's gone, then we're going to start with acetate in our dissociation equation. So over here, we have, this is the conjugate base from before, and here's acetic acid. but the acetic acid is 0 because neutralization is complete. But the conjugate base, this acetate, is a legitimate proton acceptor. So it is going to accept a proton from water, leaving hydroxide behind. Now, you do need to remember from one of the very first lessons, like if you have, you can convert between Ka and Kb. So since we are doing the conjugate base, you need the Kb. So we have to do that. So this Kw, this is a reference value. Okay. And you're just dividing basically by 1.8 times 10 to the negative 5. So now this number here, this Kb, 5.6 times 10 to the negative 10 is tiny, tiny, tiny. So for sure, the 100 rule is going to work. Okay, so then you get a when you solve for x this time, it's going to be hydroxide. So as always, when you have a base, there's always going to be an extra step where you have to change it back into pH. So you do negative log of 8.2 times 10 to the negative 6, and you get 5.09. 14 minus that is 8.91. So again, one more time, at equivalence point, it is not 7, pH is 7. Because the acetic acid is a weak acid, which means its conjugate base will accept protons and make the pH on the basic side of the scale. It's not because the sodium hydroxide is a strong base. Okay, so those are the theory parts behind it are important. The neutralization math and the equilibrium math separately are important, but I'm not going to make you do them together. Okay, thank you.